introducing him. I'll start while the last people are still coming in. It's really an honor to be able to introduce Eugene Churazov to CFA. He's today's CFA Murray Distinguished Lecturer. He's both a lecturer, he's a scientific collaborator, and a very close friend. For many of you, Eugene needs no introduction, but some of you don't really know all of the work that he's contributed in high-energy astrophysics, so I'd like to take just a few minutes to describe some of the things he's done and where he comes from. He did his studies at the Moscow Institute of Physics and Technology. He was awarded his PhD from the Space Research Institute, which is also called IKI, I-K-I. In 1996, he got his habilitation degree, also from IKI. In 2008, he was elected a corresponding member of the Russian Academy. Intellectually, Eugene comes to us in a direct line from Yakov Zoldovich via Rashid Sinyayev, so he has a perfect pedigree. His contributions are very broad, and I just picked out some of the areas in which he's worked and which he's contributed. The AGN feedback that he's going to talk about today, but also such a variety of things as the discovery of gamma ray lines from type 1a supernovae, electron-positron annihilation from the center of the galaxy, variability of X-ray emission from galactic black holes, history of Sagittarius A outbursts and properties of the interstellar medium, which is a whole story by itself, and detailed diagnostics of hot clusters. He's at home in both theory and observation, and just to read you one of his titles of one of his papers, Scattering of X-ray emission lines by neutral molecular hydrogen in the solar atmosphere in the vicinity of exogalactic nuclei and compact sources. So he's really got incredible breadth. And to put his AGN feedback in proper perspective, two of his pioneering papers, one on Perseus in 2000 and the other on M87 in 2001, both came out, one before the launch of Chandrayaan XM and the second one shortly after the launch, but before there were any actual results. So this was something that really, laid the foundation for the future studies with XM and Chandra feedback. And I guess he's already going to tell us something about his connection to Steve Murray, but I also was able to look at ADS independently. There are 21 ADS listings of Eugene with Steve Murray, and I think 6 or 9 referee papers, so it's fully appropriate that we have Eugene here as our Murray lecturer, and I turn this audience over to him with his title, which is not up there, which is Why There Are So Many Successful AGN Feedback Models. Eugene.
Thank you, Bill, for the introduction. It's a real honor to be here and give this talk as a part of the Steve Murray visitors programs. That's a very special place, and very special people work there, and that having the name written across 5 projects, 4 of them completely changed how the astronomers study the sky, and the 5th one changed how all astronomers are actually doing science and reading everyday papers. That's really remarkable and just unbelievable. Yeah. So, as Bill said, my talk today is, his provocative title is Why There Are So Many Successful AGN Feedback Model. And again, without permission, I use the image of Perseus cluster. I think that the best colors to show very clearly that's the AGN here, sitting here, and it's the hot gas in galaxy clusters, and they do interact, and that's process called AGN feedback. So I should actually patch a bit my title to make sure that I'm not heavily criticized. I'm saying that the models are partially successful because there is no hope to reproduce all the complexity here. And the second thing, it's in galaxy cluster at redshift 0 to make sure that people who are working on the galaxies and in high redshift are not really complaining that I'm trying to kind of say something very, very wrong. The AGN feedback in clusters has a long history, actually. So it was sometime around 1976 when people realized that the cooling time of the gas in the centers of galaxy clusters is actually short. It's shorter than the Hubble time. And then immediately after, within 1 year, there were fully developed models of how this gas should behave, which is called cooling flow. Basically, the gas loses thermal energy in the center, and then it should flow in. And that was really just remarkably complicated model, which was dominating the kind of cores of the cluster for 20 years. And then around 2000, actually, it was changed almost immediately to the AGN feedback model. And basically, we can say that the AGN feedback model is actually offspring of the cooling flow model. And by now, there are over 4,000 papers which have the words AGN feedback in their abstract. And I must admit, I'm not going to cite all of them. And I instead will cite a couple of our papers and those which I think are important for the logic of the talk. Okay, so that let's see what happened around year 2000. There were several observational things, experimental things, which showed that we need to update this cooling flow model. And basically, one of the principal kind of question was where is the source of energy? If you would like to actually compensate cooling time, you need a lot of energy because we do see X-ray emission from the cool cores, which means we do see how the gas is losing energy. There is just very accurately, we know precisely how much energy the gas is losing. And then we know exactly how powerful should be the source of energy which is able to compensate those cooling. And the question was where this energy comes from. And the one important experimental fact is shown here. This is Hans Boehringer, the paper in 1993, showed the Perseus image taken with Rossat HRI. And you see here the AGN is somewhere here. This is emission of the thermal gas, and there are cavities there. And the contours correspond to radio emission. That was the first clear evidence that the radio emission produced by the central AGN is able to create cavities. And this is now modern image of the same thing, but kind of morphology and the basic idea is already in this plot. This was one fact, and another fact also comes from space experiment. This is the pool boiling experiment made by NASA by just actually moving the pot of water, it's actually not the water, but this freon, to the space station, and then keeping one on the Earth, and this is on the space station where the gravity is almost zero, and then just turning on heat here, just exactly the same thing. And now what you see here, the one in kind of in space, you kind of release the heat. This heat creates vapor. This vapor creates the bubble, and the bubble grows and grows in time. If you look what happens on the Earth, the same kind of power you put, but now you have gravitational acceleration, so that when you form the bubble, the buoyancy will tend to rise the bubble, right? And the heater tries to just make bigger and bigger bubble, but the buoyancy forces are trying to remove it. And as you can see, actually, now you see a sequence of bubbles, and they all have calibrated size. It's just interplay, it's competition between the buoyancy force and the power of the heater. And so this means that if you see the bubbles, like cavities we saw in the previous image, you can immediately infer what kind of power you need, because we know the gravity in galaxy clusters. We know that how stratified is the atmosphere, right? And that the idea that by observing the sizes of bubbles, you can immediately infer how much energy the AGN puts in. And that was the idea behind the first papers about this. And so that basically that the competition between the buoyancy time scale and the inflation sets the power of AGN needed to inflate those bubbles. And unfortunately, that movie which I showed wasn't available at that time. And it took really almost a year to go through the referee to convince that this is exactly what is happening. Instead of sending him a link, just look at this, it's there. Well, and the same thing was just first observations of Chandra of the Hydra 8 cluster, basically produced the same kind of estimate. It's here, there's a comparison between the just expansion of the bubble again and Rayleigh-Taylor time scale, which is going to crush the bubble and just break it in parts. That was good because now what we can see that there is a hope that we found a source of energy. Basically, we see just from those simple estimates that the power provided by AGN is of the order or larger than the cooling losses of the gas, right? And so if you write this AGN power as the m dot c squared times f, which is f smaller than 1, that's what AGN is producing. Now, the next step, you have to take this energy and convert it into heat. So basically, you have to heat the gas. And the minimal successful AGN feedback model should assume that, well, the heating, which is the energy released by AGN, times the coupling efficiency of this energy with the gas, should be of the order of X-ray luminosity, observed X-ray luminosity, right? So that's quite simple. So the only thing you have to worry about that this factor shouldn't be too small. Indeed, you know X-ray luminosity. You know that the typical age of the cluster is Hubble time, maybe divided by 2 or whatever. And so you can multiply, you can actually calculate what will be the mass of the black hole if it was running and compensating cooling losses, Lx, for actually Hubble time. And because m dot depends on those factors, you end up with the just simple estimate that if the cooling losses are at the level of 45 ergs per second, and the product of those two factors, both of which are smaller than 1, are of the order of 10%, then you will have to grow the black hole all the way to 2 billion solar masses. 2 billion solar masses, that's okay. But if you make this product is 10 to the minus 3 or something low efficiency, then it will have to 10 or 100 billion solar masses. So you need to keep efficiency high. Otherwise, it will contradict what we know about the masses of the black holes, right? But that's kind of a hope. So as long as we have high coupling efficiency and this factor is not too small, which is said by equation physics, we can make at least simple kind of successful model. Of course, this is just part of the story. The full model should answer the set of questions: how the gas gets to the black hole, what is the physics of accretion, in what form the energy and momentum are released by the black hole, and what fraction of energy is dissipated and how. And finally, one of the important questions is whether the gas actually cools or not, as in original cooling flow model. And I'm going to concentrate on those two things. And the principal question I would like to answer is, what is the coupling efficiency of the energy which is released by the black hole to the gas? And so this is eta, and I want the eta to be as high as possible to make everything economically sound. So you just drop 1 gram onto the black hole, and you want to get most of it to compensate cooling losses. Okay, so the trouble is that there are many options to choose from. There are many uncertainties how the black hole can release the energy. And here is our today's energy release menu, and you can choose whatever you want. That column is my favorite. For you, it's today's special. So, but just let me name a couple of options. You can release the energy in the form of radiation, or it can be mechanical. You can do it in the form of rare and powerful outbursts, just explosion in the center, or you do it quasi-continuously, like the heater I showed you before. You can inject thermal plasma, like winds from the AGN, just baryons, hot enough. Or you can use relativistic particles. You can have collimated high momentum jets, or you have low momentum, just quasi-isotropic injection. You can spread the cosmic rays and mix them with the gas, or you can confine cosmic rays in the bubbles, like we saw during initial stage in Perseus and other things. So you can generate sound waves, or you don't generate sound waves. I prefer those answers, but, well, that's kind of, it's my personal preference. Now the question is whether just by choosing, you can choose whatever you want, whether the output of your choice will affect dramatically your predictions. And the answer is no, because only some of those choices actually affect our predictions. And actually, this is actually not strange. I can give you just everyday life example of this. So what will happen if I go to the Harvard Square in the middle of the day and drop $1 on the pavement and then come back 30 minutes later? And then there are the questions: where is $1? And the answer is, suggested answer is gone. And then I put here the 90% confidence. Originally I wrote 99% confidence, but then I thought maybe in Cambridge people are special, so that, well, that's 10 percent that's still there. Now, the more difficult question is who took actually $1? Was it a student or Harvard professor or somebody else? Or maybe it was Wind who carried the dollar all the way to the Charles River. And here there is uncertainty, we don't know. Just based on there are many more students than Harvard professors, probably students is more probable than professor, but still we don't know. And then the next question, which is relevant also, where this $1 is going to be dissipated. So the possibility that in nearest Starbucks, or just somewhere in Cambridge or in Boston, in Massachusetts, in USA. So I put here arbitrary numbers. And the only thing, I'm not claiming that 50% of them really going to be spent there. But the point here that those numbers are large. They might be just close to 1. Yeah, that's it. And what is the similarity with agent feedback models? Why there are so many? So many because we don't know which particular physical mechanism is responsible for dissipating the energy released by the agent. But what we know why the model is successful, because we have this answer. So all the form of mechanical energy which you put into the fluid is going to be dissipated anyway. So I'm going to just elaborate this a little bit more. So that's kind of more complete and messy version of the same kind of argument. Here is AGN, here is the heat. So we want from here, the AGN release energy won't end up here. And here is the green circle. This means that the energy is lost from the system. And then there are many boxes, and there are many people behind those boxes, and many simulations. And, well, let me start with a simple one. Suppose that AGN is just releasing the energy in the form of photons. Because our nearby clusters are actually optically thin, the Thomson depth is 10 to minus 3 or 10 to minus 2, fully ionized medium, so that the photons are just going through without much interaction. The only process which is important is probably Compton scattering, which is again scales with the Thomson depth, and the efficiency, coupling efficiency is 0. Or not 0, but very, very small. So that all this energy is going to be lost. All your radiative output is going to this circle, which means that you are not really compensating for gas cooling losses. Now, if you release it in mechanical form, there are just various options. For example, you can just inject thermal plasma, just plasma which is hotter than the ICM. What will happen, this plasma will mix with the ICM, and then you just immediately get heating, because you just add something very hot to something which is trying to cool, mix them, good, you just have 100% efficiency. You can do the same if you, for example, instead of releasing thermal plasma, you, for example, can release in the form of instantaneous outburst a huge amount of cosmic rays. Then you will drive shocks. Those shocks will shock hit the medium, and then you have a similar situation. Now you have shock-heated plasma, very hot. You mix it with ICM. Again, you are done, 100% efficient. You can consider more elaborate scenarios. So my favorite are just slow, quasi-continuous energy injection. In this case, you don't create shocks at all. Instead, you just inflate bubbles and filled with cosmic rays, and then you have just important decision. You can either confine the cosmic rays within the bubbles, so you completely isolate them. There are just bubbles thermally decoupled from the rest of the gas, only mechanical interacting with them, or you mix cosmic rays with the gas. And then, again, there are a couple of options. For example, if cosmic rays are mixed with the ICM and they are streaming, they are going to excite waves. Those waves are going to be dumped, and you again, all the energy goes to here. If the cosmic rays are confined, so they have isolated bubble, what happens? The bubble rises, steers the ICM, you can excite waves or turbulence, and again, all this goes to heat. Right? So that if you can analyze all of them, and most of the routes, mechanical routes, are actually ending up here. So This means that there is kind of a qualitative statement that all radiation is lost from the core and all mechanical energy is dissipated within the core. And this statement is valid for clusters, president cluster, and this statement is almost model independent. It's basically conservation laws and simple arguments. And I put tildes here to make sure that I'm not criticized to be too precise here. Well, and I put tildes in particular because I know a couple of exceptions. For example, if you have strongly collimated heavy jet, it can pierce through the entire cluster and end up depositing kinetic energy somewhere far away. Right? We do see radio galaxies with the megaparsec long jets, which are not really heating. Once you have a channel, well, the energy can flow through. Or if the cosmic rays are not streaming, but they are diffusing like test particles, then there are no coupling at all. So they just diffuse and leave with their initial energy. But there are observational arguments against this and theoretical arguments against this. So I would say that majority of scenarios are still fall in this category, which means that we can collapse our previous picture into something much more simple. So that's basic prediction. Radiation goes away. All mechanical energy is dissipated. And moreover, this coefficient which we worry about is of the order of unity. Well, and I used to kind of show the cup of coffee, 15 years ago, that you don't care whether the fluid is viscous or not. You don't care about properties. If you stir it with a spoon, all the energy will be dissipated within this cup of coffee, right? And that's basically the same thing. Okay, so now let me just a little bit elaborate and talk about two scenarios which are all about internal waves and sound waves. So my favorite scenario is this one. You do everything slowly. You create bubbles of cosmic rays, then they rise and dissipate all the energy in the form of heat. But there is another route when you create shocks and sound waves, and well, the shocks lead to immediate heating, but sound waves can actually, linear waves can propagate longer, and maybe they can hit different parts. So I like this scenario. I have the arguments against this scenario. I will just present them. But this is just one version, so it's just my personal preference. Doesn't mean that this is necessarily true. Okay, so that if we go along this scenario, what we end up with the cosmic rays confined to a bubble, right? And so that's the thing. Well, we are somewhere at the bottom of the potential. Well, we create those bubbles, and those bubbles are rising in the atmosphere driven by buoyancy force. But because they're essentially massless, they are filled with cosmic rays, their mass is tiny, which means that, well, if you just try to apply a force to the body with the mass equal to 0, it's going to accelerate to infinite velocity, right? It shouldn't happen, and it means that the buoyancy and drag forces acting on the bubble should be equal to 0, right? Which means that the bubble should reach terminal velocity when the buoyancy force is almost exactly compensated by the drag force, right? And if this is so, then we know that, well, every time the bubble rises, the potential energy associated with this bubble is going to be transferred to the fluid. So because the drag is actually acting from the point of view of the gas, the bubble is acting on the surrounding medium. And this means that after crossing several pressure scale heights, actually all the energy associated with this bubble is going to be dissipated. And this is guaranteed by conservation of energy, rather than something else, rather than particular physical process which is playing a role. And what actually, as I said, it's only conservation law, but we still want to know which particular physical process is responsible for generating this drag. And we can say that in normal hydrodynamic, it might be viscosity. There are viscous stresses at the boundary. We can generate turbulence in the wake. There are maybe magnetic stresses. You can uplift, actually, some of the heavy gas and carry it together with the bubble, or you can maybe excite sound wave, or you can excite internal waves. So the drag will be sum of all those components and maybe something unknown. And the only thing we know that this sum is equal to the kind of buoyancy force. And the one which is dominating, this is the most interesting question. And now the question is that maybe we should just simulate it from first principles, right? Just take hydrodynamics, make a bubble, and see what happens, right? So the first simulation we did was in 2001, and this is Zeus 2D 200 by 200 grid, and this is what I called record low resolution simulation of the buoyant bubbles. And the point is that because of such low resolution, the viscosity is high, and so that preserves actually the shapes of the bubble, and it maintains kind of shape for the long period of time. Now, of course, now we can do it much better, right? We can just use higher resolution, better chords, etc. So that, and then asked Volker once, oops. Microsoft has encountered a problem and needs to close. Okay. No. Well, this is something else. He wants just this. Yeah, better. Yes. Okay. So that when Volker Springel finished developing his wrapper, I asked him to simulate exactly the same configuration using 3 different setups. This is fixed mesh, this is moving mesh, and this is SPH, right? So you see that behavior is different, and now you can just answer this quiz. Which simulation is correct? Fixed mesh, you will get 5 points. Moving mesh, 6 points, because kind of it's for the same number of cells, it's going to have higher resolution. SPH, 3 points, because we know that this kind of behavior is actually a spurious effect of the density gradients in SPH. It's artificial surface tension here. All are wrong, 7 points, because we really don't know how they kind of model properly ICM, and I don't know, this is probably the best answer. So we really can't simulate it from the first principles, because we don't know really what we should put in. This refers to the properties of the gas itself, and especially to the what is inside the bubble and how the magnetic fields are organized, etc. Okay, so it's actually ironically, so here we know that this, from the point of view of hydrodynamics, pure hydrodynamics, those two are going to be more correct. This is going to be wrong. But ironically, if you look at the Perseus image, it's actually look more like SPH stuff with the just bubble maintaining its integrity rather than the pure hydro simulation. And so this, of course, led to a number of possibilities. Well, somehow some of the images were lost here. So introducing magnetic field with various configurations, large scale, small scale, inside the bubble, outside the bubble, and also viscosity. Apologies for Chris Reynolds, because, well, Microsoft decided not to show it here. But so that all this variety, and we don't know what is the right answer. Okay, so still the final answer that the energy dissipated is right, but the appearance of the bubbles might not be right. Okay, now I'm just going to concentrate on actually more interesting thing about the role of sound waves and internal waves in all these mechanisms. And there are many people which are actually assuming that you generate shocks, you generate sound waves, and sound waves are actually dispersing or just distributing the energy across the core. Well, I'm trying to just argue that the internal waves are doing the same. And, well, so I'll just put the couple of arguments why I think so. And what is important that in order to generate sound waves, the best phase where you can do this when you inflate the bubble, you change the volume, and that's what drives the, in order to initiate sound waves, the best way is just to change the volume. And internal waves, you can actually, the best generate them using the rising bubbles. So that for that, the best scenario is short outburst, and for that, it's going to be quasi-continuous energy injection. And you can ignore the rest for a while. Okay, let's first start with the pure hydrodynamic, no magnetic fields, stratified atmosphere. And in stratified atmosphere, it supports two kinds of waves, sound waves and internal waves. And this is dispersion relation. This is wave number multiplied by the scale height of the atmosphere. And this is the frequency divided by the Brunt-Wasserler frequency. And Brunt-Wasserler frequency is basically the frequency of oscillation of the piece of the gas which is displaced from the equilibrium, just doing something like this. So if you have high frequency branch where everything is happening so fast that the gravity is not able to kind of push the fluid elements back to the equilibrium position, and if everything is happening slowly, so the gravity is able to restore quasi-equilibrium configuration. So you can just play in the pond with this and see, well, it's of course surface waves, but very similar to this. And this is the example. So you have pulsating source. You change the volume, the sphere, and then the sound waves propagate. And this is what happens if you just take a bar and move it in the fluid, and then the energy will flow in this direction, and actually the phase velocity is going in the perpendicular direction. This is ugly waves with the phase and group velocities actually orthogonal to each other. And every time you have to use, well, 2 or 3 fingers to understand what's going on. That's admittedly unpleasant waves. But basically, this is for fast modes, this is for slow modes. Okay, let's first ask the question whether, if you look at the Perseus image, for example, whether it looks like there are sound waves there. Right? This is the image itself. This is Chandra image. Now let's divide it by such a suitable spherical symmetric model, and you will see the residuals which look like, well, the circles there. Now, do they look like sound waves? Well, let's compare with the simulations of Mateusz Łuszkowski, where he was injecting energy in the form of jets, and then you see those ripples. Those ripples are just sound waves propagating away. Does it look similar? I would say yes. Those ripples looks like those things. But the question is actually relevant, is what fraction of energy goes into those ripples? You see that apart from those ripples, you actually inflate huge cavities here, which are shown as white. Those are filled with the cosmic rays or whatever stuff you put in a jet. And the question is whether those things are just taking most of the energy, or most of the energy goes into the ripples. Now, the next question is whether the same image looks like the stratified turbulence or internal waves, which are associated with much more gentle motions. And I can't provide just numerical simulation, but instead what I did, I took the simulation of the atmosphere, stratified atmosphere of our Earth, from those people who are professionals in this, and then I just rubbed it in GIMP, right? And now this, it also looks similar, right? And the key point is that in stratified turbulence, and there is correlation length in horizontal direction is much higher than horizontal rate, correlation length in vertical direction. And this is what you see, right? You see longer structures which are narrower along the radius. It doesn't prove, but so that we have two basically interpretation, and both at the first glance look consistent. Okay, what about now? Let's try to efficiently excite sound waves. What you can do, you can assume that you have homogeneous medium, and this is the point where you're going to kind of release the energy, and the amount of energy is E, and you're going to release it during time TB, time of the burst. Now, this total energy defines you a certain size of a sphere which contains the same amount of thermal energy of the gas as the amount of energy you release. That's a sphere. You can calculate the sound crossing time of the sphere, which is RE divided by the sound speed of the medium. And this TB divided by TE, duration of the outburst divided by the characteristic sound crossing time, is the key parameter which defines everything. Well, so you can just consider two limiting cases. Suppose that you release energy over a very, very long time, much longer than TE. This means that you are just very peacefully inflate the bubble. You don't generate any sound waves. You just like inflating balloon slowly and surely. And so all the energy go into the thermal energy inside the bubble plus PDV work you do on the environment. No sound waves at all. That's the one long outburst, quasi-continuous outburst. That's what happens. So the opposite limit, the duration of the energy release is so short that effectively you have the instantaneous explosion, right? Then you can go to Zildovich-Reiser book and read what happens if you just make explosion in the small area. And there, you know that actually the debris of the explosion occupying very small region, unlike this one. And you generate very strong shock because you release a lot of energy into small volume. And this shock is going to be just dissipated around, just shock heating the gas, and most of the energy goes into this shock heated gas. But there is possibility that fraction of energy in the form of sound wave will go away, right? And so that what you can do, you can just do simple 1D simulation and calculate how much energy goes away. And this is what is shown here. This is the ratio of the duration of outburst to this TE sound crossing time of the sphere, which contains the same amount of energy, thermal energy, as the your total energy release. And this is the fraction of energy which goes into various forms. This is the bubble enthalpy, this thing. This is the shock heating of the gas, this thing. And this is the sound waves, which are going to large distance from the center. And all those estimates are done, well, long after the outburst ends. And what you can see that for the very short outbursts, you're dominated by shock heating, while you have a little bit of bubble enthalpy generation, and you also generate a sound wave, or just weak shock, which go not to infinity but to large distance, and it carries only 12.5% of energy. Now, if you increase the duration of outburst, by the time you are somewhere here, you see that the kind of the enthalpy fraction goes up, but the shock heating goes down, and the shock's sound wave amplitude stays the same. And once you reach this level, well, all contribution except for the bubble enthalpy are going down, right? Now, what we can do, we can just take observations, and actually just from observations, by measuring the radius of the shock, by measuring the jump of density at the shock, therefore the Mach number, and by measuring the ratio of the volume occupied by the kind of piston or debris of the explosion and the radius of the shock, we can derive all the parameters. In particular, we can derive the ratio of TB divided by TE. And for example, for the Perseus, it happens to be around 1, which means that most of the energy actually goes into enthalpy, and only a small fraction, which doesn't exceed 10%, goes into sound wave, right? So that you basically inflate the bubble and it captures most of the energy. But a little bit of sound waves are indeed present. Okay, that was the main argument why I don't think that it's really easy to excite sound waves. If you want to excite sound waves, you need something which is oscillating the volume, which increase the volume and then decrease the volume. That would be efficient. But with the jets, you usually only increase the volume, and that limits your efficiency. Okay, so then the conclusion, for example, for Perseus is it's likely that most of the energy actually goes in, not into the sound waves, but into the enthalpy of the bubbles. Basically, you inflate the bubble, and it carries most of the AGN output. Now the question, what will happen with this energy? Now let's go back to the dispersion relation for the waves in the stratified atmosphere, pure hydrodynamics. And the question is, what are the conditions required to excite internal waves? The conditions are simple, so you have to be somewhere in this part of the diagram. You have to move slowly enough so that you can excite internal waves. And the efficiency of the excitation should be function of the Froude number, which is the ratio of the velocity of the body divided by the size of the body and divided by the Brunt-Wasserler frequency. Basically, it compares the time scale associated with motion with a time scale associated with oscillations. If this number is less than 1, the gravity is able to take a role and excite internal waves. If it's larger than 1, you have troubles. Okay, so that how we are going to estimate? Let's consider a spherical bubble, which we put in the atmosphere, and let's calculate. We know its size, we know the Brent-Pascal frequency, we can calculate what we need, we can calculate velocity. Let's assume that the only drag which is acting on the bubble is just normal hydrodynamic drag, which is described by this familiar formula. This is density of the medium times square of the velocity times the area, front area of the body, and some dimensional coefficient of the order of unity, right? So that if you plug the numbers, if you assume that the drag is only due to this, and you plug the numbers, you will end up with the conclusion that the sphere produces always the Froude number larger than 1, which means that it's not going to excite internal waves at all, right? But if you look at this image, it's not a sphere, it's something flattened, right? Let's now replace this sphere with some flattened body. What happens that if you just keep the volume, the buoyancy force remains the same, but now you have much larger area, right? And the drag is going to be larger just because this factor is becoming larger. And therefore, you're going to slow down the object. Once you slow down the object, the Froude number can become smaller than 1, right? And that's the idea. Okay, let's do the simulation so that the simple, well, let's see, so that it shows only part of it. Okay, I will skip it. So, but basically the idea is there was 3 simulations shown with different shapes, and the one here really moves very fast, and those which you can't see, but you have to trust me, so they are moving much more slowly. And this is, of course, actually this, we do expect them to move slower, because here we do not preserve the volume. So the buoyancy force is smaller for those one. But what you can do, you can calculate effective drag coefficient, which is, oh, let me just, why just, somehow it's one movie per time. No, okay. So that basically this is what we do here. We show the square of the kinetic energy. So specific energy, kinetic energy per unit mass. And so that this is unstratified case and this is stratified case, which you can't see. But I will show you instead of the movie. What you're supposed to see is the pattern like this, right? In the case of unstratified medium, you have basically potential flow around the body, which we know is normal hydrodynamics, and possibly turbulence in the wake. In the case of stratified medium, you generate this kind of Christmas tree pattern there. And this is analogous to what ducks and, well, military ships or any other ship is doing in the water, right? This is Kelvin waves. And they are set, it's actually remarkable that this angle is the same for this and that, right? And this is set by the requirement that the pattern generated by those waves is stationary in the moving frame together with the duck. And this is exactly the same thing, slightly different dispersion relation, but exactly the same thing. You expect to generate the structure like this. And what you can do, you can actually calculate whether the change in the shape is affecting the drag coefficient. Whether kind of when you flatten the bubble, whether it immediately increases the drag to such level that it will excite internal waves instead of just normal turbulence. And this is what's shown here. This is the drag coefficient, well, for the just simple simulations, and there are 3 types of objects moving. These are rigid bodies, just for simulation. So for the sphere, the drag coefficient is roughly what you would expect for a sphere in the unstratified fluid. And they are moving with the just buoyancy velocity. And for flattened bubbles, the drag coefficient increases dramatically. So which means that there is another kind of form of drag is happening, and you can actually show that this drag, extra drag is actually coming from the, you see that the extra structures which are generated by the bubble. And what you can do, you can also show that once you generate those internal waves, well, here is a potential flow on stratified fluid. All the energy is actually confined to the narrow region next to the moving bubble. Once you excite internal waves, they tend to spread to the sides. And this is shown here. So that if you just, this is the, as the bubble rises, we calculate the fraction of energy which goes beyond the these boundaries around the bubble. And it goes with time, which means that, well, you continuously, the energy leaks to the sides, which is good for the cooling flows because you just rise the bubble here, but in principle, the energy is able to spread. Okay, and what is important that, well, that's again not movie, but static picture. The pattern, the velocity pattern is going to be dramatically different depending on how quickly the bubble rises. And in principle, all this could be measured provided that you have good angular resolution and good spectral resolution, so you can map these structures. You can not only map the velocity field, you can, for example, determine exactly the Froude number, effective Froude number for this object. Because as you see here, for the potential flow, the region of influence extends, well, far from the body. Here, the gravity is able to push the gas back to its equilibrium position, so it's just pushing this boundary closer to the body. And all this, in principle, can be measured and prove or disprove which type of waves can be excited by the moving bubbles. Okay, so what is missing, as I said, on the observational side, we want to measure gas velocity around bubbles. We want to measure line broadening as a function of radius. We want to measure correlation lengths in radio and tangential direction, and eventually full velocity power spectrum. Right. So we saw a kind of preview of those velocity measurements with Hitomi. So now we have XARM in 4 years from now, right? Approximately 4 years from now. Now we'll have Athena and Lynx from 1x years from now, so that you can ask people here what is the precise number. And then it's really might be a game changer, changing issue, so that's what is missing, and that's what we hope to measure. And so in terms of the again sound waves and tone waves scenario, what is interesting that, well, the predictions are just very straightforward. For the sound waves, the velocity field should be mostly radial, which means that when you're looking just toward the center of the cluster, you see the kind of full velocity field. Once you're looking tangentially, you just see almost nothing, only just projection of the velocity onto the line of sight. But for the internal waves, they are mostly tangential. So the special pattern of the velocity field should be spherical symmetric for sound wave and bubble centric for the internal waves. There should be, in principle, no turbulence necessary associated with sound waves, but here it's going to be character of stratified turbulence. And line profile is going to be boxy for sound waves and roughly Gaussian for the internal waves, right? And so that we are just kind of, I think we're arriving to the conclusions. I think that AGN feedback, the model is robust. So if AGN feedback can provide the energy much less than X-ray cooling losses, that would cause dramatic consequences, which we know that they're not happening. But once the mechanical energy of AGN is equal or larger than X-ray luminosity, there is kind of, that solves the problem, but then the difference between different models is actually relatively subtle. We have to go deeper. There is nothing dramatic. So this means that it can keep many people in business for decades until we measure gas velocities for good, or we understand how to model the ICM in jets. And so that it's, at the end, it's going to be this and or this, number 3 or number 4, plus brains here and plus brains here. And I would say that, well, I don't think that we will have full answer based on just simple description. But once we have the new measurements, we might be able to improve on this side as well. And I'll stop here. Thank you very much.
Now you're all true believers. So anyway, questions for Eugene.
Have you thought at all about, holding in, say, for example, Charm or whatever it's called now, and Athena and Lynx, you have parameters like the collecting area, you have the spatial resolution, you have the ability to measure velocities to a certain precision from the spectral resolution. So what are the key combinations of capabilities that one needs, keeping to somewhat low redshift objects, at least in the beginning, to try to resolve between the different ideas?
Yeah, probably you want really precise answer rather than just the larger effective area, better angular resolution, better spectral resolution, the more precise we are going to have. Well, so we actually, because there are a couple of white papers associated with Asian feedback are under work, so I think that there it will be answered. Part of the answers are just given in the Athena work, which is kind of have lower resolution, angular resolution in particular, than the Lynx. And there, of course, you are going to be limited by this angular resolution. So there is clearly just a, factor of few more you can gain with the high angular resolution, keeping similar kind of effective area. But the kind of correct answer, quantitative answer, I will just can send you probably in 2 weeks from now. Yeah.
Can I ask another question? I think the first or second, one of the early slides you showed, there was a paper you wrote with Bill Christine and maybe Boehringer in 1999 April. It was submitted, but it wasn't accepted till 2000 February or something. So the predictions were being made in the paper before Chandra was launched, but the paper was actually published after Chandra was launched. What was in play there? You remember 20 years ago?
What the reason, or?
Yeah.
The reason, the first referee, I said that, well, he is surprised with this paper given the quality of the authors. Well, I don't know, so you can interpret this. So, the second review was, there was, I think we were mentioning the analogy with the kind of atomic explosions and things like that, and then which are forming the toroidal structures. And the same reviewer said that he doesn't believe that those structures should be formed. And so eventually we asked for another reviewer, and that was just easy, right? He said, well, oh, nice, well, everything works well. That's the story. But you never know, right? So that kind of, yeah.
Well, you know when you get better data.
Yeah, but at that moment the data were really sketchy, so we were not sure that we are telling the truth ourselves, right?
Can any of this be done in the radio?
Oh yeah, so the radio is absolutely, that was only combination of radio with X-rays, which explained everything. Because actually, if you look at the, for some time with X-rays only, that was thought to be the absorption feature, right? It's only once the relatively low frequency radio images become available, you see, you can see that there is radio coming from here. Because what happens that once you populate it with relativistic electrons, you have, of course, synchrotron losses, Compton losses, plus adiabatic expansion associated with the just rise here, the high pressure region, you rise up. And so they die quickly, in particular because of expansion, which is supposed to lower the magnetic field, Lorentz factors of particles, and you can't see them very far. You need to kind of reignite them to see them far. But that's absolutely, the radio was crucial to understand the picture.
With radio continuum, is there any hope of radio spectroscopy adding to the dynamics here?
You mean, for example, 21 centimeter line in absorption? Or you are just talking about something else? Because there is molecular gas, there is also neutral gas, and people are just looking at the distribution of the velocities. The non-trivial question is how the velocity field of those denser components actually correlate with the hot gas, right? And this is non-trivial. There are filaments actually which are shining in soft X-rays. There shining in the optical lines and also in radio lines. And this is very interesting, but still also unsolved problem how those filaments are maintained for a long time. They have very short cooling time. And whether there is exact one-to-one relation between the velocity field of the hot phase and the cold phase. Because they are overdense, they can be falling in and they can be rising. I think that there are good arguments say that they're rising actually. Some of the sort of filaments you see here, and other filaments are here. And those are just studied in all wave bands.
I'm trying to understand to a degree what you meant about the internal waves creating boxy line profiles versus sound waves creating Gaussian ones. I understand what you feel about the velocity field.
Yeah.
Like if you imagine like a bunch of ducks moving through the ITM, and then you have this.
Yeah, you should do.
And that's like a radial profile, whereas the sound waves will just expand.
Yeah, I think I have this picture, might have this picture here. Yeah, basically, if you have sound waves, what you have is just radial variations of the gas velocity, right? Which means that if you are looking through the center, you see one part of the gas moving towards you, another part is moving away from you. In this case, you expect to have the very boxy shape of the line, right? Because, well, you only see the gas towards you and away from you when you're looking at the center, right? That makes the line boxy. And for the internal waves, they're just everywhere tangential things with different projections, and then you have kind of more Gaussian style lines. That's the answer.
So, Eugene, if you have access to both angular and spectral resolution, you look at the sweeples and Perseus. If they are sound waves, they are propagating in the plane of the sky, right? So the motion
Yeah.
would be like zero.
Yeah. You have this.
And internal
Yeah.
waves would be oscillating.
Internal waves are supposed to be anywhere in tangential direction.
Right,
Yeah,
so-
absolutely.
So you can much more clearly distinguish between internal waves and sound waves if you observe
Yes.
with
but-
microcalibrar with a nice.
Yeah. For example, here, this is the kind of weak shock here. So if you're just looking tangentially, you're supposed to see zero velocity, right? If there are motions at the surface, then you should see motions which are just into the screen. Yeah. But you have it in your presentations, right? In the initial presentation, yeah.
So the question is, when the cooling flow problem first appeared, I think Andy Fabian was making a point that from spectroscopy it looked like cooling flow proceeds as expected from hot temperatures to something like 1 keV, and it's at 1 keV phase that's where you need to stop cooling. So he was making arguments that you need, the successful models, they need to deposit heat into relatively cool medium, but
Yeah.
not hot medium.
So-
Is it still the standard wisdom? And if so, I suppose some of the scenarios you outlined do not do that.
Well, the standard isobaric or isochoric, whatever you want, the cooling flow model assumes that you start with the high temperature and at the very low temperature, and you have to emit, just crossing from one temperature to another, all this energy has to be emitted with the characteristic spectrum. And then there were it's clear from XMM grating data that important lines, the oxygen lines, and some iron lines of L-shells are missing. So which means that, there are two options. Either you stop cooling at temperatures lower than something, or you bypass somehow this, and the smart idea was mixing at that moment the hotter gas with colder gas, and you immediately lower the temperature just beyond that range, characteristic for those emission lines, right? In the pictures, which I assume it's actually, the temperature, typical temperature of the gas is always relatively hot, right? And there are filaments which are present there, but so I think that they are not really cooling from the ICM all the time. They might be just recycling many times, they are surviving, like they are flying around, we see them, but there is no direct evidence that they're actually cooling all the time from the ICM.
I guess my point is if you simply concentrate on balancing the cooling in the hot phase,
Yes.
you deposit all the energy in the hot phase, and you don't have cooling from hot phase down to 1 kV. I
Yeah.
thought with XMM, they spectrally saw lines which correspond to like 2 kV gas, 3 kV gas. So it looked like the cascade was going on.
Up
as
to
expected, up to like
up
1
to-
kV, and
yes.
then
the standard rule of thumb is 1/3 of the higher temperature, right? So that you have somewhere peak temperature characteristic for the cluster, and it goes to 1/3. But so it's clear that you can't have in the bulk of the gas or significant volume the temperature, say, 1/5 of the large temperature, because this would mean that the pressure will increase just catastrophically in the center, right? You have the potential well, you have the certain gravity, right? You can't fill it with the cold gas, because then the density will be just, scale height of the atmosphere will be this one, and you will have exponentially rising density, and everything will just explode. So the stable system shouldn't have a lot of gas. It might be not pressure supported things which are flying around, and that's, I think, what is happening. So I think that this 1/3 is set by the bulk of the thing and the condition that potential is fixed by somebody for you.
One last question, go ahead.
You emphasized that the feedback models are very degenerate, and I was wondering about that flow chart you had showing the different feedback ideas, and whether the morphology and velocity observations would be enough to distinguish between those various channels, or we need something else, for example, any direct probe of cosmic rays, for example?
Well, yeah, well, so that the problem is that we have now a set of nice images, right? And many of them, they look nice, but we still don't know, for example, the question whether the cosmic rays are mixed with ICM or not. There are models which assume that there are channels, so that there are magnetic lines which are connecting this. For example, in the tails of the bubble, this Chris Promer and his colleagues, they are going out and then mix. And then you can set a limit on the amount of cosmic rays in the ICM because of the pi zeros which are produced by the interactions, right? And the way out of it is either confine cosmic rays to the bubble, then they don't interact with the thermal medium, or you use streaming to dump the energy from the cosmic rays so quickly that they're not able to produce pi zeros before they die. So we actually don't know what would be the crucial element which will tell us that is exactly what is happening. So, unfortunately, and the velocity field is clearly missing. Whether it will just answer all our questions, I don't know. But as I said, so really just not enough heating will just change the picture completely, and we will see it immediately. The star formation, the cold gas, well, violent things. But once you just go into that regime, it's within the uncertainties, huge uncertainties we have on the description of the ICM, and we don't know how the jets are, actually how they operate and what is the content. That's a trouble.
Eugene's going to be here the rest of the week. If you want to look for him, you haven't signed up on his schedule. It was circulated earlier this week by Akko Bogdan, and he's up on the 4th floor. And let's thank him one more time. You have to go back to a PC if you want to use PowerPoint. So you didn't want to learn about the radio data would actually let you receive. Yes. Hit him one more time.
Good to see you. George. Yeah, thank you.
Very, very beautiful talk.
Thank you.
One thing you didn't touch on, or maybe you didn't, I just couldn't catch it. In these bubbles, which are magnetically confined, right, if you're changing, as the bubbles are moving through the medium, they must be at some from drag force being compressed. Are they? In which case,
Yeah.
or some of them at least,
Yes.
in which case do you get
Boost.
renewed particle acceleration in the bubbles?
Well, maybe not even
Yeah.
acceleration, but the adiabatic compression.
Yeah,
If it
yeah,
happens,
yeah,
it
yeah.
will just boost magnetic field, boost Bohr's factors,
sure,
it should show
yeah,
up. But usually, so if we start
Yeah.
things further down,
Yeah.
at the bottom of the potential wave,
Yeah.
usually their motion is associated with the expansion.
Right.
They are moving subsonically,
Yeah.
so the pressure drops, so they're normally getting
Getting
bigger,
bigger, yes,
and then
yeah.
they are just becoming fainter and fainter.
Fainter and fainter, yeah.
Even if we ignore some cyclical losses and inverse
But this would show up presumably as an effect in the radiant, would it? You'd be seeing a changing expression?
Yeah, so that people do see that they're becoming steeper and fainter. With
So
time.
they are expanding.
Yeah, and that's the trouble why it's difficult to kind of capture those bubbles further away. And now, so actually, the recent development was that for the one of the clusters, SPT, actually was measuring the Churazov decrement. If its thermal electrons are not relativistic electrons, in pressure equilibrium with the environment, SZ effect should be just similar to the gas. If it's relativistic particles, not anymore. And what they see that, well, they need the energy of electrons inside, at least 500 keV. So it must be relativistic particles. I can't say about protons, but at least electrons has to be relativistic. Which is, but it's messy thing, but yeah. It's like with accretion, right? So it's after initial kind of, people know approximately how it works, but then
The details.
details just
So
still
this way.
absolutely, yeah.
Great. Well, I look forward to seeing more of you this week.
Yeah.
Great.
So I was gonna, if nobody had asked you questions, and everybody did, I was gonna ask you, what's gone wrong in the Phoenix cluster?
Well, so that there are always exceptions, and well, we
There's
shouldn't.
not always exceptions, but
Yeah.
the Phoenix cluster's interesting.
Absolutely, yeah.
You know, it's got, I mean,
Huge star formation and everything. So
Yeah.
it means that it's possible. It means that, well, somehow there is no, all those rules are
but there are
working
no
on average.
bubbles, there are no, I keep
Yeah,
thinking.
the AGM is just doing something wrong, well.
Yeah,
But you know that the AGM doesn't care, right, about what's going on. It sees what something is dumped on it. Maybe it also depends on the magnetic field or something, but then it reacts. There's something is wrong with this. Just
I was actually thinking, I've never really looked at all of the Phoenix X-ray data, and I was thinking, I mean, I thought it was a good job, I don't doubt him, but
Don't know the answer to that.
yeah. Right. So, yes, it's spectacular. Yes.
yeah, it is absolutely spectacular, but I just, you know, it is
Something went
such an
wrong.
extreme,
Yeah.
yeah, anyway.
So
we should
it
think
may
about
mean
yeah.
that once something
A lot of
goes
the things we're
wrong,
working on directly now
everything is just very different from other
probably
clusters.
Yeah,
That's
yeah.
because probably we
Yeah, he
didn't.
talks about this runaway cooling flow
Yeah.
center.
Well, there is an
Because there's
interesting
nothing
paper
to stop
coming
it.
out now.
But so that's good because we see that if we don't maintain balance,
What's that
then
group
we
that I declined to-
evolve into this state. And
Right,
right,
haven't done
sometimes, right?
anything.
Yeah,
So we can't really miss.
It's a giant arc in X-rays.
yeah.
Oh, yeah.
Anyway,
Yeah.
You're probably on that.
No, I'm not, but you should.
Hi, Benedict.
So welcome. Great talk.
So we talk tomorrow.
Exactly. Absolutely. I just need to try actually my laptop real quick for a talk. That's why I came up to try my laptop on this
Okay.
projector because
Okay, so
I have
just
to give a talk in
so
20
you
minutes.
see that the old version of Microsoft PowerPoint doesn't work well. One movie per slide.
There is
Just try to show
there is basically zero Microsoft software on this laptop, and for a good reason.
Microsoft free laptop.
I try to be Microsoft
So
free.
his real question was, you had questions at the very end, and the question is whether the radio can actually distinguish. Either not today, but, on a shorter time scale than FINA, whether they detailed structure of the, you know, of a rising flattened bubble, for example.
Well, one of the things which is really just present, whether the cosmic rays diffuse or just spread across the ice layer, whether they're just really always confined to the bubbles. And usually for the energy, people care about.
I saw a star explode.
If somebody can say that there is 100% sure that electrons are confined or they're diffusing, we know that the boundaries are sharp in energy center, right? So at all frequencies, this is the same boundary.
I saw a star.
Across, there is not much diffusion light.
I saw a star explode and send out the building blocks of the universe. Other stars, other planets, and eventually other life. A s-
I've seen the beautiful center images, right?
Yes.
Those are,
I saw a star.
they're just a lot of things, but it's, I don't know. We don't know how to interpret them properly. So there are more details than we can kind of except for the just general argument that there is something is moving and then something is twisting, and, yeah, but not something which is kind of quantitative thing.
So the question I was gonna ask you that everybody else took up the time, but, you know, in the end, you make it all so simple, right? The feedback has to be working. But it took so long. People fought it for so hard, for 25 years.
But because there is, well, I remember arguing this in 2001. So
Yeah.
that they're going to hit. They are small, but
Right.
yeah, they are small. They are tiny compared to the volume. Compared to the volume.
I mean, the naive idea is, well, that, you know, it all comes out in a jet and it gets lost.
But for a long, long time, people knew that there were, they didn't see the
Radio.
bubbles in their X-ray, but they did know there were radio waves there. That they did know.
Yes, but so I think that, well, already this the Hans paper, that could be already said. All this about the
On the HRI, yeah.
because there are clear signs, energetic, clear that the radio is pushing. Well, what was new, the radio is pushing the X-ray gas, which means that there is real mechanical interaction.
So I would have told you that even in 1980, the radio data should have been good enough for someone to say that you inflate relativistic cavities, even predict that you should see the cavities. But no, I don't think anybody did.
Well, not 1980, but 1985, yeah. The VLA wasn't working in
Okay, when they started to see, you know, double radio lobes inside clusters, then they should have, in principle.
Well, I enjoyed your talk. It was at a level which I could understand it all the way through and still learn something, so.
Thank you.
Nice presentation.
Yeah. Okay, then you're giving a talk tomorrow.
No, I'm giving a talk right now, but this is unrelated. This is about ISM modeling in Illustrious and so on. This is like a smaller talk series that we do at the ITC. But I'm having trouble with my movies, which is extremely annoying, as always.
You have troubles too?
Well, now it's... God damn
I
it.
mean, the colors are screwed up.
No, it was just not playing earlier, and I'm sort of very confused.
Yeah.
I saw a star.
So now it's working. Oh, come on. Okay, this is crazy. I don't know. We'll just have to see if this is going to work or not.
So is it star formation now?
Yeah, in 15 minutes.
So two star formation. Two star formation talk?
That's right. So it's Shmuel Bialy, who actually knows something about the ISM, and me, who doesn't really know anything about the ISM, but I was asked to talk about the ISM anyway. So can figure out which half you should probably attend. I think it's going to be entertaining though. All right, good. Seems to be working now. Perfect.
Good. Okay. Then see you tomorrow.
So you're building the whole week?
Yes. So where?
That's a good question. Does Alexei have his own office? Yes, she does, right? And we should meet there. Because, you know, it's always really difficult to find quiet spaces around the ITC or anywhere else. So I'll just meet you after Alexei.
Yeah. Perfect.
Smell that pizza. Amazing. I just went out to go. Considering there hasn't been pizza here in 3 hours, it's still